Hello, thank you for watching this video. So in this video I'll be doing question 6 of November 2023 question paper, Physical Science paper 1. This is the Doppler effect, right? So I'll read question 6 statement and then proceed to answer the questions that follow. So let's go. 6.1. An ambulance is moving away from a stationary listener with a constant velocity of 25 meters per second. The siren of an ambulance emits sound wave at a frequency of 550 Hz. The listener detects the frequency of these sound waves to be 512.64 Hz. Ignore the effects of wind, right? Let's read this thing again. They are saying an ambulance is moving away from a stationary listener with a constant velocity of 25 meters per second. The siren of an ambulance emits sound wave at a frequency of 550 Hz. The listener detects the frequency of the sound waves to be 512.64 Hz, right? Ignore the effects of wind, no problem. So we'll start answering the questions. 6.1.1, the first question. 6.1.1, state the Doppler effect in words. So they want us to state the Doppler effect. So essentially they're asking, what is the Doppler effect, right? So as you might know by now, the Doppler effect, it is the observed change in frequency of a sound, right, due to a non-zero velocity difference between the source of sound and the observer, right? So it's more like it's the observed change in frequency of a sound due to an existing velocity difference or non-zero velocity difference between the source of sound and the observer. So I'm not sure if I have to write that down, but I'll say Doppler effect is the observed change in frequency of sound due to the non-zero velocity difference between the source of sound and the observer. So the Doppler effect is observed if there is a velocity difference or non-zero velocity difference between the source of sound and the observer, which means you need to have the relative motion between the source of sound and the observer. But if the velocity difference between the source of sound and the observer is zero, that means that there is no difference really, because it's 0 meters per second. If both the source of sound and the observer are stationary, or the source of sound are moving, source of sound and the observer are both moving at the same velocity, that would mean that now the velocity difference or the relative velocity between the source of sound and the observer is zero, right? So that would mean now you would not be able to observe Doppler effect there, right? You only observe Doppler effect if the velocity difference between the source of sound and the observer is zero. That's it. So I said that Doppler effect is the observed change in frequency of a sound due to the non-zero velocity difference between the source of sound and the observer. So this non-zero velocity difference, I think is very important, right? Because this non-zero velocity difference tells you that there is a relative motion between the source of sound and the observer, which means one object is moving relative to the other. That's what we need to observe Doppler effect. So now if there is no relative motion or the velocity difference is zero, there's no relative velocity between the source of sound and the observer. So you need this to exist, which is that non-zero velocity difference between the source of sound and the observer, in order to observe Doppler effect, or in order to detect that change in frequency of the sound. No problem. So we move to 6.1.2. So they're saying use the given information to calculate the speed of sound in air. So they want us to use the given information to calculate the speed of sound in air. No problem. So we know that for Doppler effect, our formula is V, frequency of a listener or the observed listener is called V, plus or minus velocity of a listener over V plus or minus velocity of source times the frequency of the source. This is our formula for Doppler effect. So here we have the frequency of a listener. Here we have the velocity of a listener. We have the velocity of the source. We have the frequency of the source. What we have, this V here and this V here are the same. This is the speed of sound in air. It's what they want us to find. Because on 6.1.2, they are saying use the given information to calculate the speed of sound in air. So they want us to calculate this guy here. Right, okay. So what do we have? We have the velocity of the source. The velocity of the source is 25 meters per second, right? We also have the velocity of the listener, because we're told that the listener is stationary, so it's 0 meters per second. No problem. What else do we have? We have the frequency of the source. We're told that the siren emits sound waves at the frequency of 550 Hertz. And we have the frequency of the listener, that the listener or the observer was detecting a frequency at 512.64 Hertz. This is the frequency of the listener. No problem. What do we want? What we want here, want the speed of sound in air, which is V, which is this part over here. No problem. So, the next thing that we do is substitute this information on this formula here. That's what we need to do. So what do we do from here? We say, okay, we have to decide if we're going to use plus or minus at the top, plus or minus at the bottom. That's the only thing that we have to decide, or that we'll have to do. So what do? We say, okay, frequency of a listener is equal to V plus or minus velocity of a listener over V plus or minus velocity of a source times the frequency of the source. So I want us to decide if we're going to have plus or minus, plus or minus. That's what I want us to decide. No problem. How do we go about this? So we are told that the siren which is the source, was emitting 550 Hertz of frequency, right? And then, but our listener, which is our observer in this case, was detecting the frequency to be 512.64 Hertz. Right, so the observed frequency is what? Is 512.64 Hertz. This is the observed frequency, which is this one, 512.64 Hertz. The emitted frequency, which is the original frequency emitted by the siren, is what? Is 550 Hertz. This is the observed frequency. It's what is heard by our listener or our observer. And this is the emitted frequency. It's the original frequency emitted by our source, which is the siren, right? So as you can see here, the observed frequency, which is the frequency of a listener, is less than the frequency of the source, which means our listener is hearing lower frequency than what is originally emitted. Because you can see that 512.64 is less than 550. So that means the frequency of a listener is smaller than the frequency of the source. That's what is happening. So what does that tell you? If the listener is hearing a lower frequency or is detecting a lower frequency, that means that our source of sound is moving away from the listener. So if the frequency of a listener is less than the frequency of the source, right? The source is moving away. That is what is happening. Because we know our friend, which is the listener, is stationary, right? The vehicle or the ambulance is the one that is moving. How do you decide if the vehicle is moving away or towards the listener? You check the frequency, you compare the frequency of the listener and the frequency of the source. And in this case, you know that the detected frequency, the frequency of the listener, is smaller than the frequency of the source. That means now that ambulance is moving away from our friend. That's what is happening. So, in this case, we say now the source is moving away from the observer or the listener. No problem. Then now, we know that this guy, which is the frequency of the listener, is lower, right? It's smaller than the source. So what do we do now? Here we must have plus or minus. Even here we must have plus or minus. So at the top here, if you want the frequency of the listener to be smaller than that of the source, you want the top part, which is the numerator of this fraction, to be as small as possible and the denominator to be as big as possible. Because if your denominator is small and if your numerator is small and your denominator is big, the entire fraction will be smaller, which means now you'll be taking a smaller proportion of that. That's what we'll be doing, because we'll be having this proportion times the frequency of the source. Now you'll be taking a smaller proportion or smaller fraction of it. So if you want the frequency of the listener to be smaller, you must make this fraction as small as possible, right? By making the denominator extremely small or as small as possible, and by making the numerator extremely small and the denominator as big as possible. So how do we achieve that? We achieve that by subtracting the velocity of the listener from that of speed of speed of sound in air, and here we add these two, because if you have a minus there, the numerator will be small, right? And if you have a plus here, the denominator will be as big as possible. So once you decide this, now you substitute everything that you have and then try to solve. That's what we're going to do now. So the frequency of the listener is what? We say is 512.64 is equal to the velocity, speed of sound in air, which is this, minus the speed of the listener, which is 0, divided by v, plus speed of the source. What is it? The speed of the source is, or the velocity, 25 meters per second, times the frequency of the source, which is 550. The only thing that you do, you solve for these guys now. You solve for the speed of sound in air. So you say 512.64, cross multiply this times that, times v plus 25, right? This is what you have. So this times this is equal to 550 times Vf times V. So you have 550 V. No problem. What do we do? Say this times this. So it's 512.64 V plus 512.64 times 25. You punch that in a calculator and see what you get. 512.64 times 25. So we get 128,000, 12,816 is equal to 550 V. Then you can transpose this to the side. What do you have? On the left hand side, you're left with 12,816 is equal to what? It's equal to 550 V minus 512.64 V. Then these are like terms. So you have 12,816 is equal to 550 minus 512.64. Okay, that this is 37.36 V. Then divide by 37.36 divided by 37.36. So you get that your V is equal to 12,816 divided by 37.36. So you get that the speed of sound in air is 343.04 meters per second. So V is equal to 343.04 meters per second. So this is the speed of sound in air. 343.04 meters per second. Okay, so now we're doing 6.1.3. 6.1.3 read as follows. If the ambulance moves away from a stationary listener with a constant velocity which is greater than 25 meters per second, how will each of the following change? Choose from increases, decreases, or remain the same. Right? So they're telling you that the ambulance now is still moving away from our friend, but now at a higher speed. Right? So they're asking you now, how will this affect the speed of sound in air? So the speed of sound in air is not affected by the ambulance, because you can think the air is everywhere, right? So if the ambulance is moving fast here, how will that affect the air or the speed of sound in air? So the speed of sound in air, as far as I remember, is mostly or largely influenced by the temperature. At high temperatures, the speed of sound in air was faster. At lower temperatures, the speed of sound in air is slower. That's what I can remember. So this, having the ambulance moving away at a faster rate, will not affect the speed of sound in air. So I would say the speed of sound in air will remain the same. That's what I would say. The speed of sound in air, I think, should remain the same, because it is not affected by what the ambulance is doing. It is affected by the temperature, mostly, largely. I'm sure there are other factors as well. So let's continue. So I'm doing B now. It should be B. At B, they're asking, how will this change in velocity or increase in velocity of the ambulance affect the frequency at which the waves are emitted by the siren? Right? So they're asking you now. They're telling you now, since the ambulance now is moving away at a faster speed or a greater velocity, they're asking you, how will this affect the frequency at which the frequency of sound waves emitted by the siren? So the frequency of sound waves emitted by the siren depend on the nature of that siren. It doesn't depend on how much the velocity, on what velocity the ambulance or the siren is moving at. So the frequency of the sound wave emitted by the siren depends on the nature of the siren, on the type of the siren. No matter how fast or slow the ambulance is moving, the siren will be exerting sound wave at exactly the same frequency. So even this one, I would say, should remain the same. That's what I'll say. Then we move to C. So, at C, that's saying, how will this ambulance moving at a higher, greater velocity affect the frequency of sound waves detected by the listener? Right? So now this ambulance is moving away from the listener now, right? At a greater speed. How will that affect the sound waves detected by our listener? Or the frequency detected by our listener. So I'll say the frequency of sound waves detected by the listener, it will decrease. Should be decreasing. The follow-up question now is probably, why did I say the frequency of the sound waves detected will decrease, right? So I'm saying the frequency will decrease because this is what they're asking you, how will this one change if this velocity of the source is increased? If the velocity of the source is increased, you are increasing the denominator, right? Which means now, if you increase the denominator of this fraction, the entire fractions become smaller. So you're taking now a smaller fraction of the frequency of the source, right? Because now it's more like you're increasing the denominator, but the numerator remains the same, right? So if you're increasing the denominator and the numerator remains the same, the entire fraction will be smaller. And if the entire fraction is smaller, now you're taking a smaller proportion of that frequency of the source, which is why the frequency of the source will decrease. So now, what I will do, I will clean the board and then we do 6.2. Okay, so now we're doing 6.2. 6.2 reads as follows. The spectrum of a distant star when viewed from Earth is red-shifted. That's what you're told. You're told that the spectrum of a distant star when viewed from Earth is red-shifted. Is the star moving away or towards the Earth? That's 6.2.1. 6.2.2. Use Doppler effect to explain 6.2.1. Okay, so I'll try just to explain what this spectrum thing means. I don't know, I can answer straightforward, give straightforward answers. That might not make sense to you. So what I'll try to do, I'll try to explain this and then see what this thing means. So, what I'll talk about white light or visible light. Same stuff, same thing, right? So, white light is part of the electromagnetic waves or electromagnetic radiation, at least that we can see, right? So, white light is a combination of these different wavelengths: red, orange, yellow, green, so white light is a combination of these colors. So this is red, this one, this is orange, this is yellow, this is green, this is blue, this is indigo, this is violet. So, white light consists of these colors. So these colors, you might have seen them on a rainbow. So the colors that you see on the rainbow, right? These colors are the colors that you see on the rainbow. So, what you need to know is that your red, the red, this part, which is this red, have the longest wavelength, right? and the lowest frequency. Why am I saying longest wavelength and the lowest frequency? You know that speed of a wave is equal to frequency times the wavelength, right? So the frequency is equal to speed of the wave divided by the wavelength. So your frequency is inversely proportional to the wavelength. Alright, so the longer the wavelength, the lower the frequency. And this side, which is this side of the spectrum, have, or maybe violet, have the shortest wavelength out of all of these colors that make up the white light or that make up your rainbow, and the highest frequency. So the red, actually this red part, or maybe this red, the red of your white light, have the longest wavelength and lowest frequency, and the violet, right, have the shortest wavelength and the highest frequency. So as you can imagine, your frequency is increasing to that side, right? So your frequency increases from your red color to your violet, and your wavelength increases to this side. So if you go to the side, you are going towards the longest wavelength. So red have the lowest frequency, and the frequency increases as you go towards violet. Violet is the one that have on these colors here that make up the white light, right? And this this one here have the longest wavelength, which is red, and the wavelength decreases, and with violet having the lowest. That's what I need you to know, is that this part of the electromagnetic spectrum, which is this side close to red, have the longest wavelength and lowest frequency, and this side close to violet have the short wavelengths and high frequencies. That's what I need you to know, right? So I'll show what a spectrum is. I'll put a spectrum here when I'm editing this video. This is where I'll put our spectrum. You will see that our spectrum will have red here. I'll try to put red here. And then as you go to that side, you'll be going towards the blue part of the spectrum. The red part have the longest wavelength, like I said there, and the lowest frequency. The blue part here have the shortest wavelengths and the highest frequency. Why? Because the frequency and the wavelengths are inversely proportional, as I've shown here. I'll put your colors here, your spectrum here, so you can understand. Now I'm leaving this part. So now, let's say now you have the spectrum here. I'll try to put a spectrum here, right? It's something similar to this, but I can't draw it with a pen. So let's say you have this is your spectrum here, right? So let me draw two of them. So these people are looking at the spectrum of a star, right? So whatever the star is that they are looking, that star should have its own identity, which means spectral lines that are sitting in a certain way, right? So, for example, let's say on a normal day, this is an example, it's not the case. Let's say on a normal day, the spectral lines, so this goes with this here, and this goes with this one down here. Let's say on a normal day, the spectral lines of that star that they are looking at, one is sitting here, the other is sitting here, the other is sitting here. Let's say this is how the star looks like on a normal day, right? So when you look at it, you see spectral lines sitting like these red three lines that you can see there. Then, when they're saying the spectrum is redshifted on that star that they were looking at, they're saying these lines that you can see, these spectral lines, have shifted towards red, or towards the red part of the spectrum, which means when I draw them here, I'll say this one moved maybe to the side, and this one moved to the side, and this one moved to the side. Because if these lines, these spectral lines that are observed on a normal day on that star have shifted to this side, which is towards red, they are said to be red shifted because they have shifted on the red side of the spectrum, towards the red side of the spectrum. So you'll find that the new line, maybe this one will sit somewhere here, and that one that was next to green, maybe sitting here next to yellow, and that one that next there is just sitting here blue. You can see that this one have moved here, this one have moved there, and this one have moved there. This is called a redshift, because your spectral lines that are known have shifted towards the red part, or on the direction of the red part of your spectrum. That's what it means to be redshifted, right? And I told you that the red part of the spectrum have what? The red part have the longest wavelength, which means highest high frequencies. And this part here, I said have the shortest. Actually, can be. If you have the longest wavelength, you should have what? The smallest frequency, because the frequency and the wavelength are inversely proportional. So if one is long, the other should be smallest. So here, you have the shortest wavelength, so you should have the highest frequency on this side of the spectrum. So, now, the star that we know where spectral lines normally sit, we can see that those spectral lines have moved towards the red part of the spectrum now when we look at the star again. What does that tell us? It tells us these lines have shifted towards the red part of the spectrum. What does this tell us? You know when you're doing Doppler effect, if you observe a high frequency, it means that if you observe, for example, we're doing Doppler effect of the ambulance. If the ambulance is moving towards you, you would observe a higher frequency, right? If the ambulance is moving away from you, you would observe a lower frequency, which is what we discovered here, because our ambulance was emitting 550 hertz of frequency, but our listener that was stationary and the ambulance was moving away from was detecting 512.64 hertz. So in this case, we can see when they were looking at the star, the light that was given out by the star was showing longest wavelengths, and which is the lowest of frequencies. Let me say smallest. So the frequency was lower than normal, because on a normal day, this is where the frequency lies, right? But now as you go to this side, your frequency is getting smaller because you're going towards longer wavelengths. So on the new spectral lines, or the positions of the spectral lines, have shifted towards the red part of the spectrum, which means now the light that have been given out by the stars is indicative of a red shift, which means it's giving out even longer wavelengths, which means lower frequencies. So what does that tell us? If you observe lower frequencies than what is actually being emitted, or maybe what we're accustomed to, according to Doppler, it tells us that the star is moving away from us. So Doppler effect is telling you that if you observe lower frequencies, it means that your source of sound is moving away from you, or you're moving away from it. In this case, our source of light, which is given out by that star, have shifted on the red part of the spectrum, which have longest wavelength and lowest frequencies. Lowest frequencies indicate that the star is moving away from us. That's what is happening. So that being red shifted tells us that your wavelength increased, which is your frequency became smaller. And using Doppler's logic or Doppler effect, that should tell you that the star is moving away from us or away from you. So if you answer 6.2.1, 6.2.1, I would say away from. So the star is moving away from us because we're observing lowest frequencies that are observed towards the red part, because I said the red part of the spectrum, has the longest wavelengths, lowest frequencies. And you know those lowest frequencies are indicative of what? Of the sources moving away. And the second one, they're saying use Doppler to explain this. Is what I've explained. You can say that 6.2.2. You can say that so red part of the spectrum, has long wavelength and lowest or low frequencies. Right? By Doppler, the observed low frequencies imply that the star is moving away from us or from the observer. That's how to do this one. Just need to understand a bit of that white light or visible light or the rainbow colors, and we're done. I hope this does make sense to you as it does to me. Thank you for watching. Cheers.